Um, Hello and welcome to the third lecture for discrete mathematics for software engineering and computer science with Master University 2020. So I hope things are going well on your end. Right? So today, hopefully things are a bit more streamlined. So as you can see from the screen I have in front of me, what we're going to do today is we're going to look at some puzzles. But what we've done before, in order to make this appealing to people who are not in computer science, so many of you are not in computer science or in software engineering. There are people in this class, who actually just want to learn about logic and discrete mathematics. Some of these people, may be from humanities. So we do want to be accessible to, we want to make everyone feel, welcome. So we're going to do some problems from the real world, all right? So some of the problems are going to be about ladies and tigers. Some of them may be a bit dated, so I'm happy to change. If you keep an eye in the chat, some people will reply and let you know that they are not from computing or software, and they do want to see other applications. So we saw a bit of linguistics yesterday. Calculations we're going to see throughout, and applications to programming throughout. But we are going to do a lot of applications to, for example, abstract algebra. So if anyone's taking math 3E03, 3E3, 2R03, for example, 3TP3, right? Any of those, right? Abstract algebra classes, I think you will appreciate a lot of the content we're covering here. If you're taking philosophy 2B03, Introduction to Logic, this class will be more than enough for your logical needs and for a particular subpart. We will not get into questions like what is truth and what does it mean to know two things. We're not going to get into those philosophical questions. We're going to do practical logic, right? How to use logic to get things done, all right? So we're going to start off with some ladies and tiger puzzles. But later in the class, and you can get the books if you like. So this is Raymond Smullyan. He unfortunately passed away two or 3 years ago. I think he unfortunately passed away, but he has a bunch of lovely books. And we're also going to use exercises from some of his other books. The books are freely available in libraries, and the solutions are in the books. But the solutions, and this will be fun for some of you, the solutions are paragraph informal proofs. And you can look at them if you like, but what we're doing in this class is making them calculational. So at one point, this was my contract job. I would read these puzzle books for fun, and I would make them into calculational proofs, just to show that it was possible. So, proof engineer, as it were. So let's begin with today's content. And so I do have an eye on the lecture. I mean, on the chat. If you feel that I'm going too slow or too fast, or you want me to stay on a particular slide, please let me know. All right. So I am keeping an eye on that. I have it open in another screen. So just please let me know if I'm going too fast for you, too slow. So bad things have happened to you, and you know what? Maybe you're a prisoner, but some bad things have happened to you, and you can get a reward. And one door has a reward behind it, and another door has some undesirable things behind it. And you need to find out which door is the desirable one and which door is the undesirable one. In this particular slide, we're saying you desire to be with another person instead of being with a tiger. But of course, you can't put your head near the door and listen if there's a roar or anything. That's just not possible, right? That's not the world we live in. So the world we live in is logical puzzles and deduction. Completely unrelated. If you're interested in how deduction can be used for computation, there's a class, Programming Languages, 3MI3, and the language is called Prolog. You use deduction and inference rules to get things done. Anyhow, so we want to find out which one of these doors is the one we will go into. And rather than hand wave it, and I won't waste your time hand waving it, if you're interested, again, the book is by Raymond Smullyan, and there's full proofs in there. I agree with you. You know what? Cool cats and kittens, tigers are pretty cool. So let's move on. Oh, I have a lot of preferable devices. Okay, so let's move on. So let's quickly review what we talked about yesterday, because I feel that we may have been in a bit of a rush, so just in case. So we talked about precedence, what to do first, right? That's precedence. And we talked about associativity, right? And that means what to do first when it's the same operation, okay? So precedence, what to do first when there's different symbols around. Association, what to do first when there's multiple occurrences of the same symbol. All right. So here is an example. Let me do a little box art for you, because I've learned how to do some of that stuff. So I thought I learned. So here is this particular one.
Prof, you're muted.
Everybody just like stop messaging it, like yeah, he knows.
Okay, can you hear me? Can you hear me again? Yes?
Yes.
Somebody, oh, we're back?
We can hear you.
Back? You can hear me. All right, you can hear me. All right, great. You can hear me. Yeah. All right. MS Teams is having a panic attack. It doesn't know what's going on, but you can all hear me. That's what I get. Flowers, yes, you can hear me. All right, great. I apologize. I don't know what happened. I think someone accidentally took control and brought it back, because someone's name did pop up. But yes. So apparently I'm not allowed to touch the other MS Teams. MS Teams is very fickle. I can only touch this one. So all right. Okay, so you can all see me. I apologize. I don't know what happened. So let's just get back to the topic at hand, and we can chit chat later if you like. All right, great. Yes. So the main difference between conjunctional, the need to have conjunctional operators is for the same reason we have precedence, right? If you notice right here, right, this bottom part, right, it involves a lot of parentheses, right? So the bottom oval involves a lot of parentheses, and we use precedence to avoid the excessive parentheses, right? But then to avoid these shared pieces, let's use a highlight. To avoid these shared pieces, to avoid the shared pieces like 5 and 5 or j and j, what we can do is make the operators conjunctive, right? So these. Oh. So this 5 and that 5, or this j and that j, or this I and that I, right? So these neighboring symbols, rather than having to write them again to repeat the same thing, we use conjunctive operators, which means we just omit the same part. This is very helpful when, for example, instead of I, we have I equals j. It seems that when trying to create a new object, you click on the previous object, highlighting them rather than creating new objects. Okay, thank you, person. All right. So, and a similar situation happens when we're talking about other kinds of relational operators. So in general, whenever you have a relational operator, like you say x, r, y, s, z, or z, what you're really saying is x, r, y, and y, s, z. Oh, my handwriting is the best, isn't it? Okay. So this is what usually means to say we have conjunctional operators, right? Notice the repeated parts, the y's, right? If this was a very long expression, you would appreciate a conjunctional convention to avoid having to repeat it. All right. So let's move on. So what we'll do is we'll write our proofs in this linear style, if you will, right? And it proves E0 equals E3. And again, just in case you forgot from yesterday, let's write up some text. So, so E0 equals E1, and then E1 equals E2, and then finally, E3 is obtained from E2, all right? And the idea is you start at the very, one day. The idea is you start at the very top, you walk along this little staircase, and then you make it to E3, right? And so that's why we say these two are equal, right? Because equality is transitive. All right. Maybe I'll just stop drawing. Okay. So because equality is transitive, right, we get E0 equals E3. All right. So here's a simple little proof. Let's see how reasonable it is to. I'll just use my mouse. Okay. So here's a simple little proof, right? Minus A is just A. Almost everyone here will have taken this fact for granted. All right. Hi. Okay. I know there's a lot of settings. Please don't kick me out. All right. So you just, from the very top, we introduced a 0 using identity of addition. 0 is the same thing as A minus A, right? Notice, because we have we're using associativity in the background, right? There should be parentheses here, and we're not going to use them, but there should be some right here. Right here. Okay. So there should be parentheses right here. But we're not going to use those, right? Because we're using associativity in the background. It's implicit. So for some of your first homeworks, what I said is you start off, so I'm reading your chat. It says you start off at the very top, minus a, and then you go to 0 plus minus a, because 0 is the identity of addition. Hello, good, all right, good. And 0 is the same thing as something and its inverse, okay? But there should be parentheses in this red box. So for the first little while, for about maybe the first month, we're gonna get you guys to explicitly put those parentheses. All right, so you cool cats and kittens will put those parentheses in there, but we're just showing it to you how it is in the book. There's no parentheses at this point. Okay, then you use associativity of addition to move the parentheses to the right side. Then you say, hey, this is just minus a and its inverse, which is 0, and then you get the a again. All right, and because it's all equalities on the side, this is the same as minus a. Then you go to the side, slide down the equalities, and you make it to a. All right. And I do have an eye on the chat, so let me know if you want to say anything. All right. Okay. We talked about how the Booleans, there's only 2 of them. Yes. There's only 2 Booleans, true and false. And equality takes any 2 values from any type and returns either true or false. Is Jim the same as James? All right. Is Bob the same as Bobbert? Is a tree the same as a flower? So equality takes 2 things and returns either true or false. And then you have these practical things, right? Nots, ands, ors, implies, equivales, exclusive or in equivalence. The last one, this negated triple line, is also known as XOR or discrepancy. Okay, it's when we're talking about different things. Right. One way to read this last one is this or that, but not both. Okay, so we'll use that in a moment. All right. As I mentioned before, triple line equality, all right, equivales or equivalence. Sometimes for you math people in particular, some of you unfortunately will also see it. It's called if and only if. And that's a really, really unfortunate way to think about it. So some people will use a double arrow like this. Okay, hardest thing ever in life. So some people will use a double arrow like this, and they will think of it as if and only if. So they think of it as 2 pieces. So whenever they want to show something as equal, they think of it as 2 pieces. This is a very frustrating thing. This is like saying 2 numbers. Oh. We'll just do some free text. There you go. So x equals y. X equals y is the same thing as x less than or equal to y and y less than or equal to x. How many people think of equality this way? All right. Does anybody think of equality this way? All right. No one thinks of equality this way in real life. Okay. Likewise, this double-headed arrow is more of a burden when starting out. Okay. You can't even see what I wrote. Okay. So this if and only if is usually a burden, right? Because it makes you think to show these 2 things are equal, I have to show this one implies the other and that one implies the other. And that's not practical. When you're doing your classes, like in first year calculus, and you say this integral is equal to 5, do you show that the integral is at most 5 and 5 is at most the integral? No, you don't do that. You try to simplify the integral till you get to the number 5, right? Likewise, we're going to use triple line equals to remind you this is just equality. and you can treat it like you normally treat equality. It's not a thing that's made up of other pieces. It just is a primitive, right? We can define implication using it, right? So, and the reason we're taking this approach is because it's way easier to work with equations than with inclusions or implications, right? If two things are equal, you can swap them around. You can do a bunch of really neat stuff with them, right? Whereas implications, not as much, right? So that's why we're taking an equational approach, right? So I hope that's cleared some things up. Right. So that, again, that's down here, right? And for now, what concerns us in today is implication is right associative. P implies Q implies R means P implies Q implies R, right? So think exponentiation, right? Exponentiation and implication behave the same almost everywhere. If you take the properties of implication and you rewrite them as properties of exponentiation, they become very, very, very familiar laws from high school. So it's a fun exercise to try out. Right. If you try it out, share with everyone else. Fun stuff. Okay. So because equivalence is just equality, so I'm just going to go a bit fast over these. We talked about them yesterday. Because equivalence is just equality, inequivalence is not equals, all right, or discrepancy, or distinct from, or distinguishable. Okay. So F is different from F? No way. That's false. Is F different from T? Yes. T is different from F? Yes. T is different from T? No way. Okay. So it's like that. Implication is if the first one happened, then necessarily the second one happens, right? So if P happens, then Q will always happen. It's always going to follow from it. P implies Q. Whenever the first one happens, the second one must have happened, okay? For us to have this lecture, it must be the case that I'm connected to teams, right? So one implies the other, all right? If the first one didn't happen, right, then we can't make, we don't know the truth about the second one at all. And so we can make any conjecture we want, right? So false implies anything. That's the first two rules. False implies false and false implies true, okay? Let's show that false implies anything. Assume you know that false. You know false. What does it mean to know false? That is false equals true. So assume false equals true. All right. If false equals true, we know that 1 equals 0 is false. All right. But we said false equals true. So 1 equals 0 is false, but false is true. So 1 equals 0 is true. Oh, okay. 1 equals 0 is true. All right. Now take your favorite proposition, all right? And we'll say, you know what? We'll take that proposition and we'll make a conjunction with false. So P and false. Well, that's the same thing as false, but false is the same thing as true. So P and false is the same thing as true. Okay. But P and false is the same as true. So you have P and false is the same as P and true, but P and true is just P. And so you have P equals true. Does that help? Maybe I'll type a little thing for you just to show you. So if false equals true, then here's P, and P is the same thing as P and true. Okay. And P is the same thing because true equals false. You can do that. And this is just P and false is just false, but false equals true. And there you go. All right. So if false equals true, starting off from false, you can get anything you want. You can show that any proposition P is going to be true. The part I was mentioning earlier about 1 equals 0 is for you mathematical cool cats, is if 1 equals 0, then you can do multiplication and say, you know what, I can show everything is equal to 0 that way. Right? And then you can get a different approach to showing any proposition is true. Anyhow, I just want to show you that. As mentioned repeatedly, we will not be uploading slides anytime soon, but there is a link to abridged course notes. So feel free to look at those and make suggestions and make use of the general chat. All right. So this is provided. So P happens provided Q happens, right? It's the other way around of implication, right? So for example, Jim is the son of Martha, means Martha is the parent of Jim. Okay, Jim is the son of Martha. All right, so going this way means Martha is the parent of Jim. Okay, so it's the converse relation. All right, so that's all. We'll see this idea of converse or flipping around repeatedly in this class. So it's just a helpful notation to think of new ideas. All right, and so that's what the very first one right here says. Consequence, right? P follows from Q means Q implies P. Right? It's just the flipping around. Okay. Yes. Lecture slides won't be posted anytime soon. Yeah. We can take that up another time. Apologies. We found that when we post lecture slides, students tend to forget that the book exists, which is quite unfortunate. There may be some lecture slides on Avenue if you look, but I won't be posting anything anytime soon regarding these. Anyhow, so here's some simple properties about implication, right? So ex falso quid libet is Latin. It means from anything, from false you get anything, right? Which we showed a moment ago. And if you have true stuff and you want to get P, well, the true stuff doesn't contribute to any new things. If you have P and you want to get true, well, true is already true, so having P doesn't matter. If you have P and you can somehow get a contradiction, you get false, then you actually don't have P. So you have the negation of P. Okay. So we'll come to these as we go along. I would like to mention that there's always a number of students in the class that will try to memorize all the theorems. Now, I don't know if you've ever played Go, chess, League of Legends, Civ, through the ages. Many games have a lot of rules to them. And if you want to do well in a game and you want to win your game, you can't always be looking up the rules, right? So you definitely need to know the rules, okay? And that's not enough. You also need to know what are the available tactics, right? How can what strategies are available to help you win the game? But if you're always flipping through a notebook, or you're not going to do well. And it's hard no one sits down to play a game and just reads the whole book. I don't know about you, but I've never read a whole manual. I just said, let's play and I'll learn as we go, right? And I'll lose the first game, but that can be a teaching game. No worries. We'll have fun, we'll chat, and I'll make a bunch of mistakes, and that's okay. I'm not trying to win, I'm trying to learn, but I don't want you to bore me with a manual. And then we'll play again, and we'll play again, and then after we play a number of times, I'm like, I got the basics. No need to explain to me what's going on. Let me try my best. And then I'll keep losing, and I'll lose, and I'll lose, and I'll lose. And then I'll be like, all right, why am I losing? And then a friend will point out, if you tried this little tactic, things might go favorably. And I'll be like, oh, everything works great. Right? And then I might get a book and be like, what other tactics are available to me? How else can I succeed? So likewise, in this class, memorizing theorems? No. Memorizing only definitions? No. How do you succeed? By jumping in. Right? So you have all these CalCheck notebooks. I have a link for the abridged lecture notes, but beside it, on the same webpage, there's a link to a CalCheck reference document that I've written up, which has a bunch of problems on Raymond Smullyan and cats and Dormouse and Alice in Puzzle Land and other things for you to try out. You also have the book. You can just formalize some of the problems up and try to prove them as you go. You have other books. So the only way you're going to learn is by doing lots of problems. And that's why we're going to try to give you a frequent amount of exercises. It's not that I have nothing to do. I have a lot to do. I would like to spend time on other things. But I think if we make exercises for you that are related to the lecture, then you might attend the lecture, which is okay, or watch the video, whatever. But then you might actually read the book. And then you might be like, all right, I'm getting a lot of red here. How do I stop getting a lot of red? I want some green in my life. All right. So somebody says, what if I keep losing the entire course? So sometimes when you play a game, it's really, really hard. Like Go, for example, is hard. Through the Ages, Civ, they have a lot of moving parts, and maybe you'll want some help, and so you'll say, you know what, I'm going to meet up with one of my friends and get him to help me a little bit, and she'll teach me what's going on before I play with everyone. I'll try to get more help. There's way too many moving parts. Let me focus on one part of the game. Chess has knights and queens and bishops, and if I play within a foreign deck, it has elephants, and I don't know what's going on. So maybe I'll just focus on what's a knight, what's a knight's move. Let me just try to get comfy with that. All right. Someone says, the first test I think is going to be the September the 22nd. Yes, I am saying, it's fun to play with bots. That's cool, but the human spirit is really what gets you going. I recommend you get online with a friend and be like, hey, let's try to both solve this puzzle, or let's see who can do it the fastest, right? Or let's delete the cell. So if you press the letter D on a cell, so press escape and press D, it will delete the cell. So try to delete one of the theorems we've given you and then write it from scratch, right? Be like, do I remember what the identity law is, and write it from scratch. A really, really good, effective game is read the book, and every time you see a theorem, not an axiom, a theorem, close the book, open up CalcCheck, try to prove it. You don't have access to CalcCheck, grab a napkin and a paper and just try your best. It's not about succeeding, it's about putting in the effort, right? Inch by inch, anything's a cinch, or so I'm told. All right. Okay, let's move on. All right. So we talked about Boolean expressions, and we talked about how you can find the value, the meaning of an expression by looking at its constituent parts. And expressions like a sentence, its parts are words. Words are made up of variables, which may act as pronouns, constants, which may act as names, and operators, which may act as verbs, right? And then you can say, all right, if I have variables, that is pronouns, how do I find out the meaning of a sentence? So if I say, he ate it, okay, he refers to somebody, it refers to someone else, and ate is a verb. If I say he is Bobbert and it is my cat, that would be a very unfortunate scenario, and I would no longer be friends with Bobbert. But if I say he refers to Leonardo DiCaprio and it refers to an apple, then all is good in the world, and I can check if Leonardo DiCaprio did indeed eat the apple or not. So likewise, at the very first row here, we say if P is false and Q is false, what do we know about not P? Well, Q has no effect and P is false, so the negation of false is going to be true, right? So there's false and true, and they just ping back and forth. That's what not does. It pings back and forth. That's all it does. What if I say Q and not P? Well, I know not P is true, and I know Q is false and anything is false, so this is false, right? And we can do this for a lot of expressions, and we're not going to do a lot of that, but it's important to understand it, right? You'll notice that Q and not P is part of this larger expression on the right, but in the middle, Q and not P is an expression by itself, right? And not P is also an expression by itself. So we say these first two are sub-expressions of the last one, all right? So we'll get back to that in a later time. But it's just important to realize that expressions are built from their parts. So again, this is in the abridged lecture notes and from yesterday's discussion. Regarding question on the chat, right now we are currently on chapter 2. Chapter 2 is a breeze, as is chapter 1. We will cover chapter 1.6 eventually, so no need to worry about section 1.6, but definitely chapter 1, a simple read. Chapter 2 about expressions and truth tables, so a very easy read. Chapter 3. Chapter 3 is the bulk of this class. It's a really big bulk of this class. So you want to get chapters 1 and 2 done, and chapter 3, please, get started on that. All right. So no immediate rush, but that is where we are right now. Okay. We're wrapping up chapter 2, and we're gonna start chapter 3. But you can ignore 1.6. 1.6 is for the eager beaver. Okay. So remember yesterday how I said that there's only 2 Booleans, but infinitely many natural numbers. And so to understand multiplication, you had times tables. To understand addition, you had addition tables. And likewise for Booleans, you have these truth tables. But each binary operator, binary means it takes 2, it takes 2 things and returns a 3rd thing, right? So for each possible inputs, there's 4 possible inputs at any time, right? Sorry, there's 8 possible inputs at any time, right? You can have false and false, false and true, true and false, true and true, and then you can have 2 possible outputs for each set of inputs. So you have 2 times 8 many possible functions, or 16. So this table right here is all possible operations on the Booleans, all of them, no more. All right. So the first row, the leftmost, is called always false. No matter if you give it false and false, you get false. You give it true and false, you get false. The first row is always false. Not a very useful operation. The second one is the AND operation, quite useful. And then we have some of these don't have a useful name. They're just they're not useful operations and don't have a useful name. We have equality, or you have some things like NOR, which we won't use in this class. Implication, equality, NAND, and then this one at the very end is always true. No matter what you give it, it always returns true. Here's an example of another one. This 4th column returns false, false, true, true. Well, if the first argument is false, you get false, false, you get false, true, you get true, you get true. So this operation in the 4th column is the first argument. It always returns the first argument, right? So you can go through them yourself if you like to and try to find out what operation they do. But historically, we have found the ones that are named here are the most useful ones. All right. So let's look at a simple example of how to use these things. So here is Henry had 1 son and Cleopatra has 2. So H for Henry, Cleopatra C, and then just H wedge C, right? Just to say had 1 son and had 2 sons. All right. As I mentioned earlier, right? And or negation and implication and how they're supposed to be pronounced. All right. So we won't spend much time on this. All right. So now that we've covered what we need, let's talk about this puzzle again. All right. So you want to get to the lady because why not? Tigers might not be your friends. They might eat you or worse. And you know that the first door says if there's a room and if there's a lady, right? In this room there's a lady, and in the other room there's a tiger. That's what the sign says. So this is similar to lecture 1 with Portia's casket. And the second door says in one of these rooms there's a lady, and in one of these rooms there's a tiger. Okay, not as helpful. And we know that one of them is true and the other is false. Okay, and we want the lady because why not, right? So one of them is true and one of them is false. So as we did before, we'll formalize first. All right. So we'll say R for a room, and then a number to indicate if we're talking about room 1 or room 2, and then we'll use a letter for lady or tiger. Okay. So room 1T means room 1 has a tiger. All right. So just a simple variables to keep track of these things, a matrix, if you will. And we know that each of the rooms has a lady or a tiger. That means room 1 has a lady or room 1 has a tiger, but not both. So that's what the exclusive or means, right? It means this one is true or this one is true, but they can't both be true. All right. So that's what inequality means. It means one or the other, right? They cannot be equal. One of them only can be true, right? And the other possibility is to be false. Right. So likewise for the other room. Right? So this is a very important fact. We'll get back to it later on. All right. Now, we know that one of the signs is true and the other one is false. So let's again, as we did for Portia's problem, say S1 means the sign 1 is true and S2 is sign 2 is true. Now, sign 1 is true precisely when what it says is true. What does it say? It says, in this room there's a lady, so room 1 has a lady, R1L, and in the other room, so room 2, there's a tiger. So room 1 has a lady and room 2 has a tiger. That's what sign 1 says. Bueno. Sign 2 says, in one of these rooms there is a lady, so room 1 has a lady or room 2 has a lady, and in one of these rooms there's a tiger. So room 1 has a tiger or room 2 has a tiger. Okay. We just wanted to show you this longer form, but it could have just been written as an equality. But some people might not be as comfortable. No, equivales is equals. Inequivalence is XOR. So somebody just asked, right? Inequivalence, like 3 lines with a line through them, that one is XOR, or inequivalence, or discrepancy, or different from, right? So this one at the very bottom says S1 is different from S2. That is to say, S1 can happen or S2 can happen, but they cannot both happen. Good question. All right. This formalization for S2 is long-winded, and we'll show later on in the class that these longer formulations might be more natural to model what sign 2 says, but it might be more practical to work with an equality instead of this conjunction of disjunctions. All right. So we'll get to that later on in the class as well. Okay. This is just to keep things exciting in the class. All right. So we can make a truth table to find out what's going on. Right? But we can also calculate, right, as we've done before, right? So we know that one of the signs is true and the other is false, right? So that means S1 is true or S2, but not both. That's the topmost line in this right-hand side calculation, right? Instead of simplifying, we can say, what's the definition of S1 and S2? We open up what S1 says and we open up what S2 says, and now we try to simplify even further. Okay. If you get stuck and you're like, I don't know what to simplify, you can always do a truth table, right, and see what's going on, right? So, but truth tables are not going to take us far in this class. Truth tables, maybe just 1 more week, and we'll almost never mention them again, just to get you comfortable and with the idea of multiplication tables, as it were. Okay. All right. So we know that S1 inequivales S2, right? Or S1 differs from S2, okay? I jumped all my steps. That's okay, all right? So the very first thing we do is we say, let me get a little cursor. Let me not. The first thing we'll do is we open up the definitions of S1 and S2, which are shown for you on the right-hand corner right here, okay? So I jumped a bit, sorry about that. But what I'm doing here is we're using the longer form of S2, right? So this time we've used the negations from the previous slide that says a room has a tiger or a lady, right? So before we said, S2 said room 1 has a lady or room 2 has a lady, but if room 2 has a lady, it cannot have a tiger. So we replaced that really quickly. But using the longer formulation of S2, which is more natural, we can have this very involved calculation. Don't worry about not knowing what things mean. Don't worry about it. I just wanted to show you that you can have it and how you'll be able to do this by yourself in time. But using a no. Yeah. Okay. Okay. Sorry about that. So you'll be able to do this yourself in time. But notice simplifying this calculation shows at the very end, at the very bottom, that room 1 has a tiger and room 2 has a lady. All right. And all you did was you started with what you knew at the very top, and you simplified using some laws of Boolean logic. And some of you might think, oh, this is very complicated. I'll never be able to do this. Let me just discuss a few steps to show you how reasonable this is. So at the very top, all we did was, the goal is to simplify. There's nothing else to do. We just simplify from what we know. We know that one of the signs is true. So that's what we're starting with, S1 or S2, but not both. And then our goal is to simplify. That's our goal. We just want to simplify. Well, to simplify this, you can use the only thing you can do is to use the definitions. So that's what we'll do. Now, the main operation in the second formula is an inequivalence. And many of us are not comfortable with inequivalence. And so the only thing to do is to get rid of it by using its definition. All right, so we use its definition, which moves it to the left-hand side. And then it's like, okay, how do I simplify further? Just as in the homeworks and assignments, when you have a subtraction and you throw it in there, or you simplify using other rules, we say, okay, you know what? This right-hand side has R1L and R1L mentioned twice, but one of them has a not, and these two cancel out, and that's the only thing to do, so we get rid of it. And then there's an equals true, and we get rid of that. That's the only thing to do. And then we distribute this negation, turning ands into ors. That's the only thing you can do, right? So I just want to mention that it's the only thing that you can do, right? Somebody just asked if P is different from Q, is that the same thing as P equals not Q? Yes, because there's only two values. So if I have two things and they're different, then that means this one must be the opposite of that one. Okay, low and high, they must always be opposite, right? If they're different, they have to be the opposites of each other because there's only two values, right? So arithmetic is way easier with the only two values. Don't have to worry about infinitely many numbers. So I'm running out of time, so let's try to wrap this up. So I just want to get back to where we started. This is, okay, still here, good. So a proof is a story. A story consists of sentences such as E0, E1, E2, E3, and then the transition between these sentences, these key plot points, are the calculation steps, right? So the calculation steps serve as transitions between the plot points in your story, okay? The way to organize these is to have expressions, which act as sentences, and expressions are formed from operators, which are verbs, and constants, such as 1, 2, 3, Jim, which act as names, and variables, such as X, Y, him, her, they, which act as pronouns, okay? And so that's why we started off with linguistics. To understand the meaning of these things, we said, you know what, this is conjunctional. E0, E1, E2, E3, just conjunctional, and then E0 equals E3, all right? So we'll get back to these repeatedly, but I hope you will all have read chapter 2. So we're essentially going to be finished with chapter 2, and we're starting chapter 3. So please at least read chapter 2 if you're not reading chapter 1. Okay. So this was a proof we showed at the very beginning. All right. And I just wanted to show it again. And the very beginning, this is a story about how double negation disappears. Okay. Unfortunately, this story starts off with a weird step. It introduces 0 at the very beginning, right? So, good morning, sunshine. I'm double negation, and here's 0, right? Okay, that might be a bit natural. Maybe you and 0 are friends, and suddenly it's 0 is these two pieces collapse together, right? So the introduction of 0 is a bit like a rabbit pulled out of a hat. All right, why did you introduce 0? Okay, maybe 0 is natural. And then 0 is the collapsing of these two. So in the book, there are proof techniques that try to guide you to making reasonable proofs, right? And proof steps. It's like when a writer has writer's block. What are the ideas to help you progress in your story, right? So mind mapping and other things. I'm running out of time, but I just I just wanted to show you, remind you that for the first little while, you must mention symmetry and associativity, but for the rest of the class, they will always be in the background, okay? But for the first little while, you will have to do them just to get you comfortable and to remind you what precedence is and what these basic operations are, because they will be used implicitly. And if things are going to be used implicitly, you should be comfortable with them first, okay? And that's what we did all the way down here in the third step. We can mention associativity explicitly this time, right? So before it was implicit, now it's explicit, all right? And I'm sorry for going over time. So again, there looks like to be a lot of laws, but please don't worry. If you practice, you'll be able to just internalize them yourself. And some of these are very silly stuff that you're very familiar with, like -0 = 0, or a minus 0 is a. So they're fun little things. You know them, they're not strange. And I recommend you practice on these integers because you're familiar with the integers. And then you'll pick up the terminology like symmetry, identity, and unary minus. And then you'll be more comfortable when we work on predicate and propositional logic. All right, then. Cool cats and kittens. Have a fabulous Friday. Bye. Oh.